All right, so here's chapter 12. We're only doing a few sections of chapter 12. If you look at the learning objectives for chapter 12, you'll see that there's not very many. And so I try to address those learning objectives fairly briefly. There's a couple other things I like to point out that's from chapter 12. So we're not going to cover everything in chapter 12. So just kind of keep that in mind. We're just going to be looking at a small segment. That's why I usually just kind of tag it on to the end of chapter 11. So when we're classifying solids, one of the things that we like to do is to look at the different types of solids. What is it that's holding the particles together? We have metallic solids. These are pretty much any metal that you can think of, steel or silver or gold or whatever, is going to have metallic bonds that hold it together. We'll talk about those in a little bit more detail here in a bit. We have ionic solids. Those are held together by ionic bonds. Sodium chloride is a good example of that. We have covalent network solids. This is where the thing that's holding it together is going to be covalent bonds. And so diamond is an example of that. And I will show that to you here in just a moment. And then finally, molecular solids, the thing that holds that together, those together are going to be intermolecular forces. So here is an example of something to differentiate between a covalent network like diamond, which is very hard and very rigid. And then over here, we've got a molecular solid, graphite, which is also pure carbon, and it is much, much different. Now, I don't have a diamond to show you, but I do have some graphite to show you. So just looking at a couple of differences here, if you look at the molecular structure, each of the carbons in that diamond is bonded to 4 other carbons. So each carbon is sp3 hybridized. If you go back and look at chapter 9, you can look at what sp3 means again. And so every one of those carbons is locked into place by the bonds with the 4 carbons around it. As a consequence, we will find that carbon, that structure for diamond is very rigid and very, very hard. Diamond is one of the hardest substances known to humans. And in addition to being beautiful, diamonds are also quite useful as an abrasive because it's such a hard substance. Now, graphite, on the other hand, you'll see here it says that it's much softer and slippery. It has a very dark color to it. You'll notice that each of the carbons in graphite is sp2 hybridized, so it's connected to 3 other carbons. But each of these sheets can move past each other, so they can slide past each other relatively easily. So I am going to demonstrate what this looks like by switching over. All right, so I've got a paper towel here because this gets a little bit messy. So this is just graphite. It's used as a lubricant. If you squeeze a little, if you got a lock that's seized up, if you squeeze a little bit of this graphite powder into that lock, it helps to lubricate the lock. So I'm just going to put a little bit onto, there we go, that's plenty. So I put a little bit onto my finger, and if you rub it, you'll find that it is very soft and it's very slippery. And so it actually makes kind of a mess. Graphite is the same substance that makes pencils work. So that's what the graphite's made out of. But it turns out graphite is an excellent lubricant because those sheets of carbon are capable of sliding past each other. And also, if you take something like oil or grease and put that into a lock, that can cause the lock to get all gunked up, and graphite ends up being a much better choice for that. So graphite is pretty handy to have around. I've got some in my workshop all the time. I don't use it all the time, but I always have some ready to go. All right, so that's diamond versus graphite. When we're looking at solids, we can categorize solids into being either crystalline, which is where they have a highly ordered arrangement. Over here on the right, we've got crystalline silicon dioxide. This is what we would see if we observed quartz. It's going to have a very regular structure. So you'll see that these atoms are these 12-membered rings here. They're very regular and repeating, and as a consequence, these form very nice, pretty crystals. Whereas, if we take silicon dioxide and we heat it up in a different way, we'll find that we get irregular arrangements of the atoms. So we call those amorphous. And amorphous just means without form. So amorphous solids are not crystalline. If you have silicon dioxide and it's amorphous, then that is going to be what glass is like. All right. So we're mostly interested in these crystals, and there are a lot of different possibilities for crystals depending on the edge length for each of the sides and the angles. And you'll notice that as we go from one type to another, all that is changing is either one of the edge lengths is different, so like tetragonal versus orthorhombic. And if we come down here, some of the angles come out to different angles. And so, and then triclinic is going to be the one where none of the edge lengths are the same and none of the angles are the same. And so that's the most complicated. In this textbook, we're going to be primarily concerned with cubic structures. And so we're simply going to look at cubic structures. All right. So when we're looking at the cubic lattice structures, there's three primary types that we're going to be interested in. We have primitive cubic, body-centered cubic, and face-centered cubic. The primitive cubic will have one atom at each of the corners of that unit cell. For body-centered, we've got one of the atoms at each corner of the unit cell and then one in the middle. And for face-centered, we've got one at each corner and we've got one on each face. Now, if we use a space-filling view of these models, so we have a space-filling view of these models, this is what they would look like. We've cut off the other parts of the atoms that are in adjacent unit cells, and so you can see how much of each atom is in each cell. You'll notice the atoms that are on the corner, 1/8 of the atom is within that cell. And with that 1/8 of the atom within the cell, and there's 8 corners, that means there's one net atom in a primitive cubic crystals. If we have a body-centered cubic, so with body-centered cubic, we've got one atom that is in the middle, and then we've got 1/8 that is at each of the 8 corners, and so there's 2 atoms within that cell. For face-centered, you'll see that we've got 1/8 of an atom that's at each of the corners, and we've got half of an atom that is at each face. And so since there's 6 faces, 6 times 1/2 is 3, plus the 1 from the corners, that gives us 4 atoms that are within a face-centered cubic. All right. Now, we've seen center, face, and corner. We haven't seen any edge. We don't see edge with these 3 cubic structures. If we had a rectangular one instead of cubic, it is possible to have edge atoms. And in that case, it would have 1/4 of the atom is present. So with this information, and knowing that these atoms are in contact with each other, there's a little bit of extra information that we can get about these unit cells. All right. So if we know the radius, we can get the edge length. And if we know the edge length, we can get the radius, provided that we know what type of cell is present. So if we want to look here, the edge length A, that is the edge length A is from one corner down to another corner. And for primitive, it's very easy. Since this is equal to 1 radius and this is equal to 1 radius, then that distance would be 2 radii. So it would be 2r. So that equation is pretty easy. For a body-centered, the math is a little bit more complicated. It's not too bad. You have to do the Pythagorean theorem twice in order to get this, but when you do that, you will get this, that the edge length A is equal to 4r over the square root of 3. And so that is for body-centered. And then for face-centered, the math is a little bit easier. You only have to do the Pythagorean theorem once, but the distance from this corner over to here is equal to 4r. And since that's equal to 4r and each of these is a, you plug that into the equation and you can solve for a, and you can get a is equal to 4r over the square root of 2. Well, we can use these numbers to calculate edge length if we know the radius, and the radius if we know the edge length. And we can even calculate the density of a particular metal given this information. So we're going to go to number 62, and this is the last one. It's actually chapter 12 instead of 11, but oh well. All right, so I still have graphite all over my hands here, but that's okay. Make sure that that is all looking good there. Okay. So now what we want to do is we've got a face-centered, so face-centered cubic for aluminum metal. How many aluminum atoms are within a unit cell? Well, again, if we've got 6 faces times 1/2, that's equal to 3, and 1/8 times 8, that is equal to 1. So 6 times 1/2 plus 8 times 1/8, that comes out to 4. So there are 4 net aluminum atoms within a unit cell of a face-centered cubic. All right, what is the coordination number? Now, coordination number, this is not a learning objective, so this is not something that you have to know how to do, but it is interesting. So I'm going to go ahead and show you how to do the coordination number. All right, so I've got a 3D printed face-centered cubic. I 3D printed this one at my own house. So here's my 3D printed face-centered cubic. And we want to know how many atoms is one atom at the face here in contact with. Well, we can clearly see that this atom right here is in contact with these 4. So that's 1, 2, 3, 4. All right. This one is also in contact with the adjacent faces. So 1, 2, 3, 4 more. So that's 8. And all right, and so now this one is also in contact with the 4 that are on the adjacent faces over here. So that means 4 plus 4, 4 plus 4, the coordination number is equal to 12. So the coordination number is equal to 12. So as far as the answer to this, the coordination number is 12. Now, in case you're curious, what about the coordination number for some of these other ones? Like, for example, our primitive cubic. Well, for primitive cubic, this one's pretty straightforward. All right. So here, if we look at this one, we can clearly see that this one that's on the corner is in contact with 1, 2, 3, but it is also in contact. So again, we're looking at this atom right here. It is in contact with this one over here. And I've got a couple more here. All right, so again, a little bit difficult to see because of the angle there. So it's in contact with one here, one there, and one there. All right, so this would be a little bit easier to see if I wasn't trying to tilt it. But the point is that it has a coordination number of 6. So if we go back and look over here, this one coordination number of 6, and this one a coordination number of 12. We think this one's got to be right in between, maybe 9. No, it's 8. But that one's actually easier to see. And so I'm going to go back over here, and I've got a body-centered cubic here that I've printed out. And if you look at that body, that one that's in the middle, it is in contact with all four of these and in contact with all four of those. And so that has a coordination number of 8. Again, I don't want to spend too much time talking about coordination numbers because coordination numbers are not a learning objective, but it is kind of interesting. All right. So assume the aluminum atoms can be represented as spheres, as shown here. If each aluminum atom has a radius of 1.43 angstroms, just as a reminder, 1 angstrom is equal to 10 to the negative 10 meters, which is also equal to 10 to the negative 8 centimeters. Now we're going to use that centimeter thing here in just a moment when we're doing our calculation of density, but that's just a reminder. Turns out angstroms are a really useful unit for measuring bond distances. So if each aluminum has a radius of 1.43 angstroms, what is the length of a side of the unit cell? All right, well, since this is face-centered, on this, A is equal to 4R over the square root of 2. Remember those 3 equations that I showed you? I recommend just memorizing those equations, which one goes with which. All right, so A is equal to 4R over the square root of 2. So 4 times 1.43 angstroms divided by the square root of 2. So that comes out to a pretty easy calculation, and we'll punch that into our calculator here. So 4 times 1.43, all right, and we'll divide by the square root of 2. And that gives us 4.044. Since we have 3 sig figs, we're going to write that down as 4.04 angstroms. So 4.04 angstroms there. My angstrom got a little weird there. Let's try that again. Close enough. Close enough. All right, so 4.04 angstroms. So finally, we want to calculate. So that means this edge length, 4.04 angstroms. All right, so now we want to calculate the density of aluminum metal. Well, density is equal to the mass divided by the volume. The mass, we're going to do the mass of 1 unit cell. So in 1 unit cell, there are 4 aluminum atoms. And then the volume, since this is cubic, we can just take this number and cube it. But instead of writing down 4.04 angstroms, in place of angstroms, I'm going to put times 10 to the negative 8 centimeters. So I'm going to put 4.04 times 10 to the negative 8 centimeters, and then we'll do cubed. All right, so that's going to give us centimeters cubed down in the denominator. Now that's going to be a ridiculously small number when we cube that, but we've only got 4 atoms, so it'll all work out. To get from atoms to moles and then moles to mass, well, first we want to use Avogadro's number. So we'll do 6.022 times 10 to the 23rd aluminum atoms per mole of aluminum. And then finally, we want the molar mass of aluminum. So here I've got my periodic table, 26.98 grams per mole. So we'll put 26.98 there. 26.98 grams of aluminum per mole of aluminum. Well, you'll see the moles of aluminum cancels out. The aluminum atoms cancels out, and we're going to get grams per cubic centimeter. All right. Now, probably the most important thing here is making sure that you punch all of this into your calculator correctly. So I'm just going to clear that, and we'll put 4 divided by, and then I'll put 4.04 second EE negative 8, close parentheses, and we want that to the third power. All right, so that's this number. Now we want to divide by Avogadro's number, so divide by 6.022 second EE23. All right, and now we want to multiply that by 26.98, so times 26.98. And that gives us 2.72, we will call it. So 2.72 grams per cubic centimeter. All right. So we've got one last, or a couple of little details here. Not one last thing, a couple little details. If we've got ionic compounds, it turns out we can determine the empirical formula for an ionic compound by looking at, here we go. All right, so we can determine the empirical formula for an ionic compound by looking at a unit cell and determining what the formula is with that unit cell. So we're going to start with this green and gray one here on part A. So A here, we've got green is chlorine. So the arrangement of those green atoms is going to be primitive cubic. So each of the green atoms is at the corner. So 1/8 of the atom is within the cell. 1/8 times 8 is equal to 1. So there's one green atom. And you'll see here that the cesium atom is right there in the middle. And so it is completely within the cell. And so that means that the ratio of chlorine to cesium is 1:1. So that means that the formula for cesium chloride should be CsCl. Now, of course, you guys could have figured this out in a different way, because I'm going to come back over here to this page, because you know that cesium is in group 1, so it has a positive 1 charge, and chloride is in group 7, so it has a negative 1 charge. And just so everybody's clear, there's cesium over there in group 1, chloride's in group 7, so it has a negative 1. So with those, since it's 1:1, you would have known you would have had CsCl. But what this method does is it provides us another way of coming up with the empirical formula. All right, so let's look at zinc sulfide. So the yellow atoms are sulfur. So if we count the number of atoms that are sulfur here, we've got 1/8 at each of the corners. This is a face-centered cubic arrangement of the yellow atoms. So 1 at each corner, or 1/8 at each corner, and then half of an atom at each of the 6 faces. So that means there's 4 of those yellow atoms that are within each cell. So the net number is 4. For the gray atoms, it's a little bit difficult to see here, but this gray atom is in between this corner and the middle of that unit cell. This one is in between this face and the edge there. And so we will find that that all 4 of the zinc atoms are within the cell. So that means there's a 4:4 ratio. So the formula it's not going to be Zn4S4. It's going to be just ZnS. It's the lowest whole number ratio. So ZnS. All right, and then finally here, the green ones are calcium. So you'll see that's face-centered. With face-centered, that's 4 atoms. The gray ones are fluorine or fluoride ions, and you'll see that all 8 of those are within the cell. So it's a 4:8 ratio. 4:8 is 1:2. So 1 calcium for every 2 fluorines. It'll be CaF2. It'll be CaF2. So that's something that I want you to be able to do. All right, one last little topic here is talking about metallic solids. Metallic solids are they're different than covalent bonds, they're different than ionic bonds. So the electrons aren't transferred, and it's not like the electrons are shared between two adjacent atoms. The electrons are shared among all of the atoms. And so your valence electrons can move freely from one atom to another. As a consequence, that means that metals are really good conductors of heat and electricity because those electrons can move so freely. All right, so they're delocalized throughout the metal. And that's what a metallic solid looks like. So kind of interesting there. All right, and I think, yes, that is the end of chapter 12. Our next chapter, of course, is going to be chapter 13. So look for that soon.